Okay, we're back and we're looking at capacitors, and specifically what happens when you put certain materials, insulating materials, in the gaps of the capacitors. These are called dielectrics. So we know that capacitors are pretty simple devices. They can be plates, spheres, cylinders, and it's two different surfaces with a gap in between where they store charge and store energy. That's just what they do. The energy is stored in the form of an electric field between the two charged surfaces. One's positive, one's negative. The dielectric, though, is something that we use in just about all capacitors nowadays. And pretty much all of your electronic devices have multiple capacitors in them. Have this so-called dielectric material in them. They're insulators. They help prevent sparking between the two charged surfaces, especially when things are so tiny nowadays. You really want to kind of protect the integrity of the device. So what we're going to try to do is specifically look at how to handle when you have a chunk of material in the gap. Now in reality, these materials would probably fill the entire gap, but let's say that you don't. Here's a little sketch of just a little slab of material, the red, in between the two plates, one positive, one negative, of a parallel plate capacitor. Now the capacitor, with the plates, whether there's material or not, it's going to form an electric field. It's going to shoot across the gap. It's going something like this, out of positive towards the negative. Now the thing is, there's no such thing as a perfect insulator. So we have to look at what happens to this material when it's placed inside this electric field. It polarizes a little bit. Any free charges, let's say free electrons inside that material, will get attracted towards the positive side, the positive plate. So you might have some negative charge build up on that surface. And when those electrons leave the right-hand side of the material, it'll have a slight little positive charge that collects. So it polarizes. And that behaves as kind of like a little mini capacitor, if you want to think of it that way. It has a little electric field which goes from right to left, from that polarized positive to the polarized negative. Okay, so what you see then is the net electric field that you have for the capacitor is that strong electric field, the original electric field, which is represented by the black arrows there. But then you have this other vector, this other little electric field, which goes the other way. And maybe we'll call that E prime inside there. And so it's a subtraction. So your overall electric field gets a little bit weaker. Physically, that's what these dielectrics do. They polarize and they make the electric field a little bit weaker. Well, what that means, if the electric field weakens, then the voltage difference between the capacitor plates will decrease as well. And the reason for that is voltage difference goes as the integral of your electric field. Okay, this is kind of a standard electrostatics relationship between fields and electric potential. So if your E gets smaller, then your delta V gets smaller. The definition for capacitance is this ratio of the charge on the plates divided by the voltage difference. Okay, so there's an inverse relationship between capacitance and voltage. So if your voltage goes down, your capacitance actually increases. And that's what, again, that's the consequence of putting a dielectric material inside a capacitor. It increases the capacitance, the original capacitance, by some factor which is called the dielectric constant. And that's that funny looking K that I have written there. These things are bigger than 1. Okay, so that's just kind of the very basic theory, physically what dielectrics do. They increase capacitance. Okay, now let's take a look at two examples of how to actually calculate specific capacitances. Now I'm just looking at parallel plates in this video. So here's a side-by-side comparison. Here's a wire. Okay, let's say that imagine electric current might be flowing down on each of these. And it goes into a capacitor, which in this first one is partially filled by this dielectric going along the length of the plate. Okay, going from right to left. This is the general expression of how to find how many farads, okay, to find the capacitance of a parallel plate capacitor. Directly proportional to the area of your plate, inversely related to the gap between the two plates, that little d. So effectively what you do in this picture on the left is you have the full area. Okay, it's going from right to left. You have the full area of the plate on top there. But you know, when you partially fill it, you only have a smaller distance for the material, and you have a smaller gap distance for the air portion. Effectively, it's kind of like going through two capacitors that are in series with each other. And the reason for that is, if you look at the original picture, you have one electric field in that top portion. You have a different electric field, okay, a different behavior in the gap where you have just air before you get to the other side. Okay, so it's kind of like you're going through this one capacitor after another in the same line, and that's series. This right-hand picture, notice it's a little bit different. Here we filled half the capacitor across the total distance between the two plates. So effectively we have the same D, okay, from plate to plate with the dielectric material, but on the top and the bottom, effectively we only have half of the area with the dielectric and only half the area on the right-hand side with air. So if you're coming down this wire and you get here, if you go to the left, you see one thing. If you go to the right, you see a different thing. It's kind of like you split it. Well, that looks an awful lot like two capacitors in parallel. C1 on the left, C2 on the right. Okay, so looking at this expression here of how to find the capacitance, let's check it out. Let's do the series one first. Let's use this second drawing. And we'll make use of our rule of how you add capacitors in series. You have to add the reciprocals of the capacitances. Again, we'll think of this as two capacitors, C1 and C2, in series. So what we're going to have to do is try to figure out 1 over C1 plus 1 over C2. Add those together and then flip it over. Okay, now I might skip a little bit of the algebra. I just want to really focus on the setup here. Okay, let me rewrite how we find capacitance for parallel plates. Okay, so C1, you have the total area, and you have a dielectric constant. Okay, so we have whatever that dielectric constant is, just some number. We have epsilon, a constant. We have the full area of the plate. But we have a smaller distance. We have a distance d1. Now C2, the air capacitor part, dielectric constant for air is effectively 1. So we have epsilon, we have the full area, and we have whatever d2 is. Okay? So that's the setup. Now it's just, we have to do some algebra, we have to do some addition of fractions and stuff like that. Okay, let's compare right away. Let's look at the right-hand side with two capacitors in parallel. Now the parallel rule is we just add capacitors together. So this is just going to be equivalent to C1 plus C2. Well, C1, using our rule, we have a dielectric constant. There's our epsilon. But now we have the equivalent of only half the plate. where you can store the charge. So I'll put area over 2 in the numerator, and that's separated by the total distance. The air capacitor, okay, dielectric constant is 1. We have epsilon, half of the original plate, half the area, but the full distance, the full gap. Okay, so that one's going to be a little bit easier to add together. Alright, so these D's are going to flip up on top. We have kappa epsilon A in the denominator, D2 on top, over epsilon A. Okay, so for the series one, it looks like we're going to have a common denominator of kappa times epsilon times area. Okay, so if we add those two together, we're going to get D1 plus kappa D2 all over kappa epsilon times area. We have to flip that over, and we get the total capacitance. First example on the left, we'll have kappa epsilon A all over D1 plus kappa D2. On the right-hand side, the parallel set over here, okay, again, here's our pictures. We already have the common denominator, so we can do this in one step. Let's see, we're going to have common factor of epsilon A over 2, and then we'll have kappa plus 1 all over the gap distance. And that'll be the total capacitance for that parallel set. Okay, so that's what it looks like when you have these dielectrics and they're just partially filled capacitors. Now keep in mind, you can always play games with this. We could do something just really silly, like, I'll just sketch a real quick picture here. Maybe you have a variety of different kinds of dielectrics that you put in here. Okay, where maybe in this region you have kappa 1, you've got kappa 2 in another, and you have another material, kappa 3, in that portion. Who knows what those distances are? Up here on this side, we only have half the area. So what would this be equivalent to? Okay, I'll give you a second to think about that. Well, it's kind of like you change colors. If you're coming down this wire here, the first portion, if you go down you see one thing, if you go up you see another thing. It's kind of like you split. You're going to have two capacitors in parallel. Okay, this would be your kappa 1, this would be your kappa 2, D1 and A over 2. But then those kind of recombine and you go through this region. So that's kind of like you're in series with that one. And so whatever that material is, you have the full area, okay, with whatever that gap distance is. So that would be kind of like two in parallel connected in series with the third one. Okay, I'm not going to work out the algebra for that, but you kind of get the picture of what we're doing here. Okay, so with these two examples, and this one kind of crazy one just for kicks, hopefully you kind of see what to do when you have these things with dielectrics and only partially filling the actual original capacitor. And yeah, then it's a bunch of algebra. Okay, so hopefully these dielectrics aren't too bad. That's really about the extent of what we're going to do with these in class. So hopefully you get it. Keep in mind, physically you're polarizing the material, and that weakens the electric field, decreases the voltage, increases the capacitance, and then we can actually calculate these things. Okay, so I hope this helps, and until next time, we'll see you later.